have a doozy on our hands with this one here. My name is Drew, by the way. I'm a tutor with Wyzant. I tutor multitudes of topics in mathematics. So we're asked to find the area of the following set where k equals this set right here for all x in the real numbers such that x squared plus y squared is less than or equal to 1, 0 is less than or equal to y, which is less than or equal to x squared, and x is greater than 0. I mean, this is a little bit redundant because you kind of have that. Well, no, you don't actually, because this can be negative, so it's not redundant. Never mind. Anyway, so the best way to kind of think about this is first determine what area this is talking about. So first things first, this here should look familiar. This is the equation of a circle, which has a radius of 1. So let's just say 1 is about here. I'm not going to be drawn to scale, but you get the idea. So we have a circle that's about this area here. Or it might be better actually if I do this here. Yeah, that's better. Let's just call that the circle with radius 1 here. I'm just going to move that into place. Yeah. Alrighty then. So what it's asking for here is everything inside of this circle, because we're looking for x's and y's less than or equal to 1. So we're asking for all the interior of the circle, for which is what this is talking about here. The second part right here, it says that we're looking for x and y's that are positive. So both, or rather that y is positive here. So y is going to be greater than or equal to 0, but it's also going to be less than or equal to x squared. So if we think about y equals x squared, if we look at just this part here, y equals x squared, we're looking at everything that equals this and is less than that. So if we can kind of draw here, not to scale by any stretch of the imagination, but we're going to do that. And that's kind of a parabola here. So this is y equals x squared, and there's that circle that we were talking about. Alrighty then. So, and then we're also asking for all positive x's. So the x's that we're looking for are all positive. This is x and this is y. So that means that the x's are all going to be toward this direction. So we're only looking at quadrants 1 and 4. For this one here. Now this one here says the y's are all positive. So now we know that the x's and y's are positive. So it's only in the first quadrant that we're looking at. But we're also looking at y's that are less than x squared. So we're looking at y's that are underneath this graph here, underneath this parabola. And then lastly here, we're looking for everything that's inside this circle. So when we connect all that, we're looking for stuff inside the circle, underneath here in the first quadrant. So what we're looking at is this area right here. Now, the reason this is a doozy is because of how we have to set this thing up here. So in order to figure out what we need to do, we just need to figure out how to separate this. Now, a good way to do it is, this is 1 here, and that's where this equation equals 1. The best way I have come up, I think, to think about this is this whole area underneath the parabola. So I'll call P that area underneath the parabola. And we're going to subtract this little area right there. And this area you can describe as the area underneath the parabola, starting from this intersection point right here to 1, so that intersection point to 1, and this parabola one is from 0 to 1. I'll just use I for intersection there. And then we're going to be subtracting the circle here, the area underneath the circle, also from that intersection point to 1. So basically we're taking this chunk here and subtracting this little piece there, and that's going to give us that piece there. So this is going to be our kind of formula, if you will, to find this shaded area. And we can find this using of course, integrals. So this is going to be the hard part here. Let's go to the next page to kind of sort this out here. So I won't go through all of the arithmetic, but we had to find where that intersection point is. To find the intersection point, you just think about the equation of that circle just on the top part. We don't have to worry about the bottom part, which is y equals the square root of 1 minus x squared. And then you have to think about the parabola, which is y equals x squared, and then find the intersection of those two things. If you plug a few things in, you'll get a quadratic equation that you can get. And you get that when they intersect, x equals the square root of the square root of 5 minus 1 over 2. It's kind of a messy number there, but that's what it is. So based on this thing that we were saying before, which is this little formula to find the area, we're doing the area underneath that curve minus these here. So that's going to give us here the integral from 0 to 1 of that area underneath the parabola minus, and we're going to do the integral from, now what I'm going to do is to make my life easier and everyone's, I'm just going to call this here, I'll call that phi. I'm doing that for a reason, kind of, because it's related to the golden ratio. But we'll call that phi for now just to make things a little bit easier, to 1 of x squared dx minus, we're going to call that phi to 1 of, now of this circle here, or at least that top portion of the circle, dx. Alrighty then. So from here, we can start simplifying things a little bit. Now I'm going to keep these integrals in place just to kind of keep it a little bit easier to look at here. Phi to 1 of x squared dx, and I'm just going to transfer in that minus sign there, 1 minus x squared dx. Now here, these are pretty easy to evaluate, even if you have this weird number there. These are pretty easy to evaluate. This is where we're going to get a little bit of trouble here, trying to evaluate this thing right here. But if you might be familiar with something called trigonometric substitution, so that's what we're going to do. We're going to let x in this integral here equal the sine of theta, which means that dx equals cosine of theta d theta. And theta in this case equals the arc sine or inverse sine of x. All right, so we're going to rewrite that with that substitution in mind. And we're going to do that, phi 1 x squared dx. And then now we're going to do the integral. I'll put the limits here in a second. When you plug all this in here, then you end up getting cosine of theta for this. And then, of course, when we substitute dx, we get also another cosine of theta d theta. And then since we're plugging these values in there, the inverse sine of that is just going to be the inverse sine of that phi. And then inverse sine of 1 in this case here is easy. It's pi over 2. All right, now we have all the things we need to work with in order to solve this problem. This ends up simplifying to cosine squared theta. And if you know your trigonometric identities, there's the power reducing formula, and that's going to give us, okay, I'm going to rewrite these, phi to 1 x squared dx plus, and then we're going to get that inverse sine of phi, pi over 2, and then this ends up reducing here to 1 plus cosine of 2 theta over 2 d theta. We can pull that half out there into the front there, and then that's going to give us, again, seems like a lot of writing, but this is sometimes what you have to do to keep track of things. And we're going to pull that half out, inverse sine of phi to pi over 2, and that leaves 1 plus cosine, oops, I put cosine 2 theta, cosine of 2 theta d theta. Alrighty then. And then everything we have here we can use to simplify this. So let's go to the next page here. All right, so let's start evaluating these integrals. So that first one, which was the integral from 0 to 1 of x squared, that's easy. That's x cubed over 3, and that's evaluated from 0 to 1. And then we're going to subtract, once again, that was that x squared. We're going to evaluate that the antiderivative is x cubed over 3. But this one here, we're going to evaluate it, that phi, to 1. And then we're going to add, now we had that 1/2 here. And so we had the cosine of 2 theta. It was theta, or rather 1 plus cosine 2 theta, so that evaluates to theta, plus 1/2 of sine of 2 theta, and that's the antiderivative of the cosine of 2 theta, and that's going to be from that inverse sine of that phi number again to pi over 2. Now in this case here, when we evaluate this, this becomes 1/3. Let's see, 1/3 minus this here ends up being, yeah, because that's a 0, so that goes away. Let's see, that's 1/3 minus phi cubed over 3 plus, now we're going to have a 1/2 here in the front. And now here, evaluating this theta gives us pi over 2. And then we're going to plug this in here. And now when we have pi over 2 plugging into theta here, we're going to get sine of pi, which is 0, so we can just ignore that. Then we are going to subtract. We're going to plug that in, so we're going to get that inverse sine. I'm using this shorthand for the inverse sine of this phi. And we're going to add, now we're going to add 1/2 sine of 2 times the inverse sine of phi. We're going to ignore this for right now. We're just going to focus on this part right here, or this part right there. Or actually, we can just focus on this part here. So we have 1/2 of sine. Now there is also another identity here that we can use, that the sine of 2x, or 2 theta, is 2 times the cosine of theta times sine of theta. So this here, right there, simplifies to 2 times. So when since we're pulling a 2, we can cancel that. So this right here simplifies to cosine of that inverse sine of this times the sine of the inverse sine of this. Now there's also another identity that we can use here, because we have the cosine of something and the cosine of the cosine of the inverse sine of this one right here. There's an identity that says that this ends up equaling 1 minus this number here squared. And then, of course, since we have sine and inverse sine, those cancel, and we're just left with that, so we're multiplying that by that. This is how you would simplify this whole thing. So, and after all is said and done, this is what that would equal. After we simplify everything, we have 1/3 minus 1/3, so these two cancel. And we're left with negative phi cubed over 3. And we're adding 1/2 times pi over 2 minus the inverse sine. So I'll write this out. Inverse sine of, now I'm going to, I am going to put the phi here. Minus, now this, once we multiply everything through, it gives us the square root of the square root of 5 minus 2. We can, of course, simplify this further by understanding that phi equals the square root of the square root of 5 minus 1 over 2, and then doing the arithmetic there. But this would be your answer. And this is what I meant by saying it's a doozy. This is quite a lot of work, mainly because we're finding the area in between here. If it was up here somewhere, it might be a little bit easier, but There we go. So you have it. Alrighty then. So good luck with this, and please let me know if you need more help. Thanks.